All right, thank you. So what I'm going to talk about, my last talk of this symposium, because of Professor Thibault's talk cancellation, will be about FAIMS applications, advances in FAIMS technology and its bioanalytical application. So the previous three talks were about the things that are already used in the pharmaceutical industry or imminently about to be used. And this talk will be about more advanced things that we hope and count on will be used within next couple of years. It's more of a capability development thing. So this work was done at PNNL, and collaborators on that are Gordon Anderson and Dex Smith. As a summary of what were major advances over the last year, and I mean within our group, and that I'm going to talk about today, are three. High definition FAIMS. What is high definition? It's a combination of exceptional resolving power and high accuracy of the peak position, so that you not only have a narrow peak, but you have a narrow peak always in the same reproducible place. Together, this provides a capability to do assignment of species just based on the position of that peak with high specificity and accuracy. That was enabled by extremely stable new voltage electronics that I'll talk about a little bit. The second development is hydrogen-rich buffers, sometimes almost pure hydrogen. And we were, over the last year, replacing helium by hydrogen in binary mixtures with nitrogen. Helium-nitrogen mixtures were a staple of FAIMS ever since Roger Gavrimon work, who discovered the utility of them over 10 years ago and used commercially in thermosystems. We are now replacing them with hydrogen wholesale because the benefits really are significant, and we have not found any single case where it would not be worthwhile to do it. This broadly improves the resolution, accelerates separation. It does avoid electrical breakdown because hydrogen is a lot less prone to breakdowns than helium, as I'll talk about. And it also augments field heating in FAIMS. Sometimes that is useful, sometimes it's not, but we'll see. And together, these two technological developments now have enabled high-resolution FAIMS of proteins. So jointly, these things allow reaching resolving power as high as 400 for protein conformers, versus just 80 using helium. So this is the greatest advantage of hydrogen in any application we have found so far. The peak widths and resolving powers are same as for small peptides. So for the first time ever for proteins, I think, we found a situation where resolution is controlled instrumentally and not by conformational diversity within apparently a single feature, which has never been achieved, I think, with conventional IMS of FAIMS, because it was always controlled by protein multiplicity of conformations. So these are what I'm going to talk about. But first of all, by way of a little introduction, Professor Kreiser already talked about the fundamentals of FAIMS in terms of the asymmetric waveform and how and why it separates ions. So I'm not going to talk about it. I'm just going to dive right into the various analysis geometries and why we use what we use. There are two fundamental types of FAIMS geometries. There is a curved, which can be cylindrical, spherical, or combinations thereof, or potentially other curved geometries. With any kind of curvature, you have an inhomogeneous field, and with inhomogeneous field, you have ion focusing. Ions are focused to the gap median, or maybe oppositely defocused, depending on the ion type, which results in multiple species being in equilibrium. So multiple species can pass through the FAIMS device, not through the same exact trajectory. Some species will pass closer to internal electrode, some species will pass closer to external electrode, but all of them will be in equilibrium at some point within the device and can pass. And commercial systems, bioanalytics, and now thermo do have that kind of geometry, and therefore they have this multiple species in equilibrium inevitably. Contrary to that, in planar FAIMS, we have parallel electrodes and the field is homogeneous. Here, parallel electrodes with homogeneous field, and you can have a compensation voltage applied to opposite plates and the dispersion voltage, or you can apply them to the same plate together. That really does not matter in principle. So, but there is no ion focusing, and there is only single species in equilibrium, and that of course means much higher resolving power potentially, because in principle you have only one species in equilibrium. Because we're interested in pushing the resolution of FAIMS forward, even at the expense of some other characteristics we always use in our planar devices and what we do. What are the factors that control the resolving power of IMS and FAIMS on the physical level? In conventional IMS, the resolving power scales as a square root of electric field and is essentially independent of the gas. So here is a well-known equation for decades where the resolving power scales as a square root of electric field, drift tube length, and inverse square root of temperature. So there aren't really many parameters to work here with, honestly. Not much you can do to increase it within the drift tube IMS. With different gases, you have different absolute mobilities, but same peak capacity. Here's a paper by Brandon Ruotolo and co-authors, which shows that with different gases for the same peptide mixture from a digest, you get different drift times, but the peak capacity is essentially the same in all cases as is shown here in this data analysis. And for specific peaks, you can get different separations by changing the gas, as for example ion composition is shown here in the first talk of the day, but those are targeted analysis. Overall peak capacity doesn't change. Contrary to that, in planar FAIMS, the resolving power scales as a cube of electric field and also square root of mobility. So obviously the dependence on electric field is always almost an order of magnitude stronger, cube versus square root at 6 powers greater. And so it strongly depends on electric field, and just by example, if you increase the electric field by only 25%, you double the resolving power, while in conventional IMS you would only increase it by about 10%. So that's what I mean, an order of magnitude stronger. It also very strongly depends on the gas. So it is high using lighter gases simply because of this term. And the gases where ion mobility is high, such as helium or hydrogen, therefore are beneficial. Further to that, separations are often better in mixtures than pure gases because of something called non-blank phenomena. So using the mixtures of helium or hydrogen with nitrogen improves separation even more than just pure helium or hydrogen would. What limits your choice of gas or increase of field? According to the previous equation, we should just increase the field indefinitely and use pure hydrogen or helium. Unfortunately, we cannot do it, and that is because of electrical breakdown. Electrical breakdown depends on the field, but it also depends on the gas. And here, it's a diagram which shows that with helium fraction increasing from 0 to 100%, balance being nitrogen, the breakdown field decreases, and particularly rapidly decreases at very high helium fractions. Initially, it doesn't decrease much, but then starts decreasing much more rapidly. The thermo device actually operates within this rectangle, and that's the optimum operating point. What we have realized some time ago, by accident actually, is that you can operate FAIMS at significantly higher voltages than the textbook tells you about the breakdown voltages in DC. And the reason why is because FAIMS uses RF. And with RF, the avalanche reverses direction before reaching the opposite electrode, so you can't so easily break down an RF field because you start breaking down and then you reverse direction in high frequency RF. But even and that's well-known effect, certainly we did not discover it, but even compared to that, you can use even higher frequency field and high voltage. And the reason why is because FAIMS filtering removes all ions from the gap. So any kind of breakdown initiator that would be created in the gap and propagate through the gap causing that avalanche is cleaned out of the gap. So that allows to use very high fields in FAIMS, significantly more than we expected. But even then, of course, there is a limit, and that limit has to be a little bit below the electrical breakdown here in blue to provide you a safe operating margin. Which means that in the end of the day, you cannot really use helium more than about 70–75% around here. Or you can use 50% helium with high voltage. So that's where we would operate using helium. It really doesn't matter much where we operate along that curve as long as we operate along that curve. And here's an example that with helium-nitrogen mixtures, you can reach over 300 resolving power for peptides. Also, like with any separations, the peak position is proportional to the elution time or separation time, while the diffusional peak width is proportional to the square root thereof. So the resolving power, and with it the peak capacity, scale as a square root of time. That applies to any separation in media: chromatography, capillary electrophoresis, conventional drift tube IMS, or now FAIMS. And indeed, with about 500 millisecond filtering time that you can achieve by adjusting the gas flow, the resolving power increases by about 60% from here to here as expected, and the resolving power experimentally increases by 70%. So the black line is 200 milliseconds, the green line is 500 millisecond filtering time, and we achieved the statistically demonstrated resolving power of or slightly more than 300 for peptides that has been published recently. So exceptional separation power possible with longer analysis, and you can in principle extend that time and resolving power indefinitely, other than of course you will lose all lines and have zero sensitivity. So this is older work by way of introduction. Let me now move to newer things that we have done more recently. High definition FAIMS, like I said, the first point of this talk. High resolution and high accuracy together make for high definition. I was talking about what limits instrumental resolving power in terms of physical phenomena. And those are very important when you have resolving power of 10 or 100. Once you go into multiple hundreds or eventually into thousands, with most instrumental analytical techniques, the resolving power becomes limited by parameter instabilities. And by way of example, in time-of-flight mass spectrometry in the 50s and 60s, the resolving power when it was 100 or 200 was limited by such things as, for example, the diffusion of ions and the spread of initial velocities of ions. But with modern orthogonal reflectron TOFs, it's not limited by that. It's limited mostly by instabilities of the pusher voltage, instabilities of the lens due to thermal expansion or contraction of the time-of-flight tube, and other things with which the designers of time-of-flight mass spectrometry fight. And those limit the resolving power at 30, 40,000 time-of-flight mass spectrometry. So a similar thing now happens, I think, with IMS work, including that of Professor Klemmer's cyclotron IMS, but also with our FAIMS, was that we became increasingly limited by the instabilities of various parameters, which in FAIMS are many: pressure of the gas, temperature, the amplitude of the waveform, the compensation voltage, and perhaps others, including the quality of the surface of those FAIMS electrodes that defines the precise gap width at every position. So we started trying to fight those one at a time, and we've built a new stabilized FAIMS generator that supplies compensation voltages with both relative and absolute output veracity of under 1 millivolt, about half a millivolt. This has just been published in JASMs. So here is our previous power supply with which we worked for years, and here's a new one, high definition. You see pretty big difference in oscilloscope trace of that voltage output that is actually deployed to the plates. And here's the result. The peak width, statistically analyzed with 53 replicates in this case, has improved from 140 millivolts to about 100 millivolts. And that is a consequence of both increasing output veracity, but also increasing definition of the voltage through the use of high digital to analog converter cards. For example, previously our step in scanning was 10 millivolts, and now it's under 1 millivolt. So together, this difference and that difference actually correspond to about 40 millivolt narrowing of the peak, and that's exactly what we see. And therefore, the resolving power increased by about 40%, and now we can statistically go from 300 to over 400 for that same exact peak I was showing of a peptides in type 2. I would make a comment here that when we compare the resolving powers in any technique, I think it is important to have a proper statistical validation through the replicates and statistical analysis of this data as to what is your confidence. So for example, here it is at 95% confidence, which means 2 statistical deviations of the average. We all know about one peak wonders that do occur, so when we claim and compare resolving powers, I think it's important to have that kind of statistical validation. That was with helium. Now with hydrogen, much higher resolution using hydrogen. The breakdown threshold of hydrogen exceeds that of helium by 5 times. So if you have a gap of 2 millimeters in pure helium at atmospheric pressure, about 800 volts breakdown. With hydrogen, 4.5 kilovolt breakdown. That is less than nitrogen. Nitrogen is about 8 kilovolt, 7 to 8, but greatly higher than helium. So that permits hydrogen-nitrogen mixtures as high as 90% hydrogen as opposed to 50% helium at this maximum dispersion voltage that we currently have of 5.4 kilovolts over 2 millimeter gap. And the compensation voltages in hydrogen-nitrogen and helium-nitrogen mixtures with equal nitrogen percentage are actually similar. So if we replace helium by hydrogen 1-to-1, we don't gain all that much. There is a slight gain possibly, but overall they're very similar. However, the difference is that we simply can go to 90% hydrogen while we have to stop at 45-50% helium. So while the curves are similar, we simply can extend those curves a lot longer. And the peaks similarly continue narrowing in hydrogen-nitrogen mixtures, just as they do in helium-nitrogen as you increase the light gas because of the FAIMS physics. Again, there is some advantage of using hydrogen simply because the mobilities in hydrogen are higher than in helium, so the peaks are slightly narrow in hydrogen, but the main advantage comes simply from being able to extend those curves to higher fraction of the light gas. So the resolving power is the peak position divided by the peak width, so you doubly gain by using hydrogen, and that's shown here, how we can go in terms of resolving power for this particular species from something like 30 using helium to over 100 using hydrogen, and for some other species achieved close to 200 for singly charged ions using hydrogen. So replacing helium by hydrogen may improve resolving power by about 3 times. That's for small molecules. You will see what happens for proteins later. So now we go back to that statistical evaluation and see what we can do for peptides. For peptides, Syntyde 2 is our benchmark peptide that we always use because it exhibits 3 charge states, 2, 3, and 4, and also has a very good intensity in all 3 charge states comparable and very sharp narrow peaks well defined with not many confounders. So the compensation voltages for peptides, all peptides, this is just an example, continue increasing with increasing hydrogen fraction up to about 90%. You can ask what happens above 90%. Above 90% they slightly decrease, and that's a consequence of this non-blank phenomena. So it is not advantageous to use more than 90% hydrogen, even if we somehow could afford it by breakdown limit. We cannot afford it because it will break down in pure hydrogen. No, we need it. So it's a very good coincidence there that our capability to operate here stops exactly where we need it to stop from the physics of separation. And we can achieve even higher resolving power. For example, here at 86% hydrogen, again with full statistical validation, achieved resolving power about 460 at 2 confidence, 2 standard deviations means 95% confidence. And a very interesting question actually is whether if we take a mean of the peak widths, don't we underestimate the performance? And that applies to any IMS or FAIMS or any separation. The reason why is that when you measure some physical quantity, like you want to measure the dissociation energy, you will make multiple measurements and take the mean, and that's appropriate. But in analytical chemistry, we often see that people say, well, I took 3 replicates and I used the best because that's the best separation. So there is some random variability in the separation and you take the best, and that's quite okay to do that. Unlike physical measurement where you don't take the highest or the lowest, you take the mean. So you of course don't want to take the one very best either, with the called one peak wonder. So what we looked at is, say, out of all these multiple peaks, actually these are not the all peaks, this is just a part of the sequence. We can usually take about 50 peaks, this is only a fraction. The mean of the best half, if you take 25 best ones out of 50 and calculate their mean, you get about 530 with similar statistics. So we think that that actually may be a more appropriate quantity for what is the best you can ever do with a separation. So anyway, the difference between those quantities tells you that there are other reasons, other variabilities, even with our high definition FAIMS. And we know what they are. The pressure is not stabilized, the temperature is not stabilized, and they create this kind of peak jitter, and some peaks are significantly wider than others. We need to continue working on improving that, and we are. But nonetheless, for the time being, this is the highest resolution, I think, for any IMS or FAIMS stage coupled to mass spectrometry. I know Professor Klemmer did something similar with cyclotron IMS, but maybe not coupled to mass spectrometry from what I've seen. If that's not correct, then correct me. But in any case, varying peak width suggests that yet higher resolving power if remaining instabilities will be addressed, and we are working on it. We think we can do even better. Now I'm going to talk about applications of this capability. And first application is localization of post-translational modifications. As an ion filter, FAIMS is best for targeted analysis, just like quadrupole. And proteomics is now shifting to characterization of post-translational modifications. Same post-translational modification often attaches at different sites, and that creates what's called localization variants. This type of isomers very commonly coalute in liquid chromatography and are not distinguishable by MS/MS. Sometimes they are, of course, but often they are not. And here's one thing that I think is very important. If you take any particular peptide, doesn't matter how many residues it has, it doesn't matter what they are. So X1, X2, X3, and X4 completely arbitrary. And you put on it one post-translational modification. Again, doesn't matter what it is. You put it, attach it to residue C, or to residue B, or to residue A. And all other residues are arbitrary, and even can be any number of them. So X2 is not necessarily one residue, but some collection of residues. Then only the peptide 1 and 3, these two sequences are distinguishable in principle by single stage CID or ATD. You cannot ever find whether this is present or not in a mixture of this, because any fragment on the left is the same as these fragments, and any fragment on the right is the same as those fragments in terms of its mass to charge ratio. So this is fundamentally indistinguishable by single stage MS. And that also applies for multiply modified sequences. So if you have, for example, two modifications, again, doesn't matter whether they're the same or different, and what is the rest of the peptide or sequence, same applies. You will only be able to distinguish one or three, but not the two. And that can be generalized further. So the bottom line is that only two localizations are uniquely identified for any number of PTMs or any peptide length. So if you have 3, 1 is not identified. If you have 5, 3 are not identified. And that tells us that you really need better ways to separate PTMs, because currently PTMs are often assigned to a protein region, not a specific residue, and we need new approaches to localize them. So we worked with Professor Kelleher at Northwestern to look at some histones. Histones is, of course, a very important, if not the most important protein. And it's also probably the best laboratory to look at post-translational modifications, because histones feature pretty much every kind of PTM imaginable: phosphorylation, acetylation, methylation, and others on multiple sites, and they're very, very richly modified. For the simplest histone H4, in principle, there are over 10,000 options how you can distribute those post-translational modifications, and about 100 were observed with some degree of confidence. So that tells you that 99% are not yet known. And most of these modifications are on what's called tails, which is the segments of about 130 for the H4 and slightly different numbers for other histones, but somewhere around 30 to 50 amino acids for most histones. And again, that's the simplest histone. For H3 and other histones, those numbers are actually an order of magnitude or so more. So histone 4, we took this piece, synthesized 125 tail. It has 5 lysines in position 5, 8, 12, and 16, and 20. These 4 are known to be acetylated in vivo. This was not known to be acetylated in vivo. And these are peptides about 3.3 kilodaltons. They make charges 4 to 7 in electrospray. And we subject them to that high-resolution FAIMS using hydrogen, between 50 to 75 or 90% hydrogen. The resolving power is exactly the same as for small peptides, about 300 at 70% hydrogen, meaning that there is no peak broadening because they are larger peptides, that they are 3.3 rather than 1 kilodalton. So they are not triptych, they are significantly larger, yet there is no broadening. At 60% hydrogen, the optimum separation is achieved, and we can separate in charge state 5 and 6. So there are charge states 4, 5, 6, 7. The best ones, right here in the middle, 60% hydrogen, charge state 5 and 6. We can separate all 4 histones baseline quite easily, in fact. We can separate K8 plus from K16 in charge state 5, because they overlap in charge state 6. And all the other 3 we can easily separate in charge state 6. So by combination of these 2 charge states, we can separate all 4 histones baseline very easily, in fact. At higher hydrogen fractions, the resolving power increases even further, but peaks start vanishing, some peaks disappear. That's presumably because of strong isomerization and what's called FAIMS self-cleaning, about which we published. So effective resolution of localization variance is possible for even larger peptides. And also importantly, the separations in charge state 5 and 6 are completely unrelated. I'll talk about that in a minute. Now, those were acetylated histones. Intuitively, one might think that variants involving smaller post-translational modifications would be harder to separate, because if the bit you're moving along that protein is small, then, well, it probably should make less of a difference. That was intuitive thinking. Turned out that my intuitive thinking was wrong. The variants involving methylation, and that is the smallest additive PTMs, that has 14 daltons, turned out to be as easy, if not easier, to separate than acetylated histones. So here we looked at histone H3, just so that we are not limited to H4 and know if what we do is more general. And monomethylated and bismethylated, so one has 1 methylation, another has 2 methylations on different residues. Again, these are biological human histones that are biologically methylated in position 4 and 9, or in this case, position 27 and 36. And we see that they are easily baseline separated in either charge state 5 or charge state 6, in this case, using 70 to 80% hydrogen. These bismethylated histones are again very easily separated at about 70% hydrogen in pretty much all 3 charge states, 4, 5, and 6, that they have strong signal in electrospray. Now, the separation is very large. It's about 25% range of compensation voltages between the peaks, and about 10 to 20% between the largest base peaks. These. So as you see, the separation is about 10 times baseline, roughly. And Alan Marshall would probably say you can drive a truck between them. But methylated variants are very easily resolved, and peak capacity does not scale with PTM mass, contrary to my initial expectations. That means that you can pretty much separate anything here, even the smallest PTMs. For perspective, 14 Dalton PTM relative to the mass of that peptide would be 1/2 of 1%. And 1/2 of 1% relative to my body weight is roughly a cell phone. So what this does is that I put cell phone into my back pocket, or I put cell phone in my left back pocket, and FAIMS would know which back pocket my cell phone is at. Now I'm going to talk about proteins, the last topic. The potential energy surface for proteins generally exhibits several major basins and many minor wells in each basin. That's kind of the overall structure of proteins and probably most other macromolecules. So here's an illustration that I pulled from somebody's Nature paper here, where there are major basins. Here's, for example, one major basin, and within that major basin there are minor wells here. So what happens is that unless you anneal things very deeply, proteins get stuck in those wells. And when you do separation, by any separation technique, you generally separate those basins, but you see a combination of wells. So for example, when you do liquid chromatography or IMS, it's fairly easy to separate elongated, fully unfolded proteins from partly unfolded proteins from folded proteins. So for example, this well, which would be native state from that well, which would be partially unfolded, from, say, something that is completely unfolded. Here they talk about amyloids, but for example, it could be completely unfolded here. What is much harder is to somehow separate those little wells within each basin or remove them. And because of that, LC separation or CE, capillary electrophoresis, or conventional IMS always show very broad peaks. So here's an example from a fairly old paper from Northwestern here, Robert Hutchins and co-workers, where you can see that separation of cytochrome C, charge state 12, 13, and 14, the peaks are very broad. And the resolving power is, based on this peak width, is about 20 to 30, while the instrumental resolving power for that instrument is about 150. That's not just theoretical, but experimentally demonstrated for other smaller species like peptides, metabolites, and clusters at that time. So as soon as you go to proteins, however, the peak becomes 10 times broad. The reason why? Well, it's because there are all these multiple wells coexisting under this peak that you can't pull away. So the question when we started our work on FAIMS, does this problem extend to FAIMS? We of course expected that it does because it applies to every other separation technique, but we decided to see for ourselves. So we long time ago did ubiquitin conformal separations, first with two-dimensional FAIMS IMS. Here are the conditions using nitrogen. That work was published a while ago. So this is a FAIMS dimension, this is an IMS dimension, and there are 6 charge states that we looked here from 8 to 13, which are most intense ubiquitin charge state. The spectra in the IMS dimension are very broad, just like expected, resolving power 10 to 20, even so the instrumental resolving power is 100, that we already know. The peaks in the FAIMS dimension are similarly broad. However, even so the resolving power in the FAIMS dimension was about 10 only, we could not determine whether it is instrumental problem or that conformational multiplicity problem. The reason why we could not determine that is because our FAIMS resolving power was similarly low, only about 10, so we did not know whether it's just instrumentally low or it is low because of conformations. So we could not answer that question at that time. Now with planar FAIMS, a little bit later, we tried to do the same experiment, and we found that the peaks narrow a little bit. So the dashed line is actually what you get with cylindrical FAIMS, and the solid line what you now got with planar FAIMS. So peaks are a little bit narrower, so the resolving power is slightly higher, about 20 here versus 10 here in the FAIMS dimension. But again, that did not answer our question. The reason why is because the instrumental resolving power is high here, but still only about 20 to 30 in that planar FAIMS at that time. So we still could not answer that question, whether they are low because of instrumental limitation or because of conformational limitation. So we kind of abandoned that question at that time because we could not find the answer. So now we came back to that question with the new technologies that we have. And here is the same ubiquitin protein. Now we start using helium, which we did not use previously. With helium, the resolving power increases clearly, as it's expected. Here's the data from 0 to 50% helium for all ubiquitin charge state from 5 to 13. That was just published last month. You would see that for all charge states, the resolution is limited by conformational multiplicity. So we got our answer now. The resolving power of that FAIMS for peptides, as I have shown, 3, 4 plus charge state is about 200 or even 300. And the maximum we ever got here for ubiquitin is 80, with these 4 peaks nicely resolved. Or you can say nicely resolved, but still it's much lower resolving power. So we know that for all charge states of ubiquitin, even at 50% helium, we now hit that limit. So we cannot achieve the resolving powers that we got instrumentally for peptides for this protein because of conformational multiplicity. Now we got that answer. And that is 80 in the best case. For other cases, it's much, much lower. You see peaks are horribly broad here. So can we do anything better? And turns out we can using hydrogen. So here are this, for the first time I'm showing you the data for proteins using hydrogen. Same ubiquitin, but now we are using hydrogen, 0, 50, 85% hydrogen. Look at the data at 50% hydrogen, which has what they are, the blue lines, right? No, what is this? Oh, I'm sorry. It's actually 0, yeah, 50 and 85%. So 50 would be green lines. Even the data are already significantly better than using helium. It's not entirely clear why in this case, unlike for peptides, the hydrogen produces significantly better resolving power and peaks than helium. Partly it may be related to somewhat stronger heating. The heating in hydrogen is slightly stronger than helium, but it's only a slight difference and it's not entirely clear. I talked to Professor Cooks yesterday. He gave me some other suggestions that it may be related to narrower distribution of relative velocities in hydrogen. I'll have to think about it. But in any case, whatever the reason, experimentally at 85% hydrogen, the resolving power is 400 for the narrowest peaks with statistical validation. And the mean resolving power of all peaks for charge state 10 to 13 is actually about 250. So even not exceptional, but the mean resolving power is significantly over 200. The highest peaks 400 and possibly even 500, but I would conservatively say 400. These peak widths are exactly the same as the peak widths for 3+ and 4+ peptide and the resolving powers, which suggests that we have reached the instrumental limit here and now not anymore limited by conformational multiplicity to a significant extent. So you can resolve as many as 10 different conformers quite easily here for this ubiquitin protein. Well, we were thinking, can we extend it to larger proteins? As you go to larger proteins, you might think that you will have more of a problem because, of course, you can have more conformers. So we looked at cytochrome C and we got very similar results. Here are charge states 11 to 20 for cytochrome C. At 85% hydrogen, we get mean resolving power for all features about 130. And for those charge states 16 to 20, which are more unfolded high charge states, you get resolving power of 200. Those are mean values. The maximum for certain peaks are 300 or even higher. Again, those peak widths are very close to those for multiply charged peptides. There are also tiny but very real and reproducible features at negative CV type A ions, which were previously found only for 30 kilodalton and larger proteins and ascribed to dipole alignment. But from some initial simulations, we think that the onset of that situation occurs earlier, and those are very unfolded conformations with very high dipole moment, which are very uncommon for smaller proteins, but they can exist and result in this type of features which are way away from the rest of them. Once you go to larger proteins, those very unfolded conformers or other conformers with high dipole moment become prevalent, and then the whole spectrum moves to negative CV, as we published previously. So the question is, how far can this approach be pushed to even larger proteins? And at this time, we have found very similar results for myoglobin just last week, and we continue pushing it up, and we'll see how far that can be pushed. But I'll show probably more at SMS. So one last point is that separations for different charge states are independent completely. Here I'm going back to my data for histones, where I have this acetylated histones 5, 8, 12, and 16. And I'm comparing the separations for different histone variants with different localizations of these PTMs for charge states 5 versus 6, 4 versus 6, and 4 versus 5, which are all the 3 charge states 4, 5, and 6 observed for that peptide. And you can see that there is no correlation. The correlation is essentially 0 in all 3 cases. So this just validates what you have seen visually, that the spectra in different charge states are unrelated, but that mathematically proves it. So why that is important? It is important because what that means is that the total peak capacity is essentially proportional to the number of observed charge states. If the charge states are independent, then it's just additive. And that number of charge states scales as the square root of peptide mass, or faster, as is well known, and increases for larger proteins. For small peptide, you see 1 charge state plus 1. For bradykinin, you see 3 charge states, 1, 2, and 3. For ubiquitin, you see somewhere around 10 charge states. For carbonic anhydrase, you see 25 charge states, and for larger proteins, you see more and more charge states. So what it means is that your peak capacity of FAIMS separation actually does increase for larger proteins in proportion to that number of charge states. And what it further means is that your capability to distinguish different localization variants, quite counterintuitively, might actually be higher for larger proteins, because simply you have more attempts, more shots at that goal, that if you did not succeed in one charge state, you can go to another and another and another, which you can't do for peptides. So that at this point is a conjecture that this type of localization variants might actually be easier to resolve for intact proteins by combining that multiplicity of charge states with extremely high resolving power in each of these charge states that we have now achieved. And if that is the case, you could do separation of different position of post-translational modification in histones completely on an intact protein top-down level, which would be quite amazing, but we'll see if that's the case. So let me conclude. The planar gap FAIMS analyzers do allow unlimited resolution in principle, but instrumental constraints, of course, limited to something that is not unlimited. However, those constraints are progressively relaxed by technology development, as I have shown you, and there is still room there further. Unlike with conventional IMS, the gas composition is crucial, and mixtures of light gases where ion mobility is high, helium and hydrogen, broadly raise separation power. But as we have seen today, hydrogen is truly magic sometimes in that respect for reasons that I myself do not yet fully understand. Fluctuations of parameters such as voltage, pressure, and temperature is important, and stabilized voltage increases resolution by up to 40% and improves CV accuracy. It will become even more important as you go to higher resolving power. So this is kind of the beginning where it becomes important. The breakdown threshold of hydrogen is about 4 times that of helium, permits 90% hydrogen at maximum separation voltage, and using hydrogen raises resolution for small ions up to 3-fold. I can tell you that we are almost not using helium anymore, other than to provide a benchmark for what we can separate with hydrogen, just to demonstrate it, but in practical analysis we don't even need it anymore. Another aspect here is the cost. Cost of helium is very high compared to hydrogen, and in many countries, not so much in the US, but in many countries that differential is even much greater. So from a practical standpoint, particularly outside of US, using hydrogen is a great advantage to FAIMS. Now, we broadly resolved the peptide localization variants even for middle-down peptides, such as histone tails with small PTMs, acetylation and methylation, including multiple PTMs. And there is no correlation whatsoever between the degree of separation you can achieve and whether that is a large or small PTM, or whether there is one or many PTMs, or what is the shift by which those PTMs is moved. And that's a great thing, because in mass spectrometry, of course, it may be not so difficult to separate shifts by 10 residues, but shift by 1 residue, where in principle there is only one unique fragment. If you ever get it, then that's a big advantage. Finally, replacing helium by hydrogen raises the resolving power for small proteins as large as 5 times, up to the instrumental limit of 400, which is the highest resolving power for proteins achieved in any type of IMS, and how far that extends to larger proteins is being determined. But it is now limited by instrumental resolving power as best as we can judge. Separations for different charge states are orthogonal, and the peak capacity scales with the number of expressed states that goes up for larger polypeptides. Therefore, the conjecture is that we possibly could separate sequence inversions or different post-translational modification variants for intact protein top-down, which is what we will try to do. So this work was funded by NIH, DOE, Battelle, others, and here are the people who contributed to it at PNNL, and also Neil Kelleher at Northwestern very much. Thank you very much for your attention.
Charge multiplied by the electric field in your resolving power expression, in which case
Yes, that's a great question. And yes, if you think that the resolving power is physically limited, yes, there is that QEV there, and yes, you should have the 4 protein peaks actually should be narrower, and the resolving power should be greater. And to some extent we have seen it. Some of the proteins peak we observed are actually narrower than any of the peaks for peptides or smaller molecules that we've ever seen. So the narrowest peaks we've ever observed in FAIMS to date are for those proteins. But on the other hand, they're not as narrow as they would be just according to the Q1/2. And so it is possible that we are still not quite at the limit of instrumental resolving power. But it is also possible, as we know, that our instrumental resolving power is limited not by QEV, but limited as we observe by those parameter instabilities, in which case it, of course, will have nothing to do with the charge state of a protein. So we can't really conclusively answer that. Well, I mean, yeah, of course you need a mass spectrometer, I mean, if that's a question, but, you know, in any analysis of proteomics, of course you will need a mass spectrometer realistically anyway. I'm not sure exactly what the question is, but yes, you need a mass spectrometer.
You're saying that there's some orthogonal information in the other charge states, and I understand that as long as you've got the charge states separated by the mass spectrometer. I don't understand that if it's just a phase analysis, but you just...
Well, what I meant is that, okay, say by way of comparison, if you use drift tube IMS and you have, well, I don't know what would be a good example. Okay, let's say fullerene. A fullerene can be singly charged, doubly charged. The separation between C60 and C70 will always go the same direction, whether they're singly charged or doubly charged. So you will not realize much additional information by looking at separation of doubly charged C60 and C70 versus singly charged C60 and C70. We know it's just cross-section, really. So the absolute cross-sections of this will, of course, change slightly, and the absolute mobilities will double if you double them, but relatively they will stay the same. I think you will have no additional information, essentially. And most of these things work like this in drift tube IMS because of that's what the cross-section is. In FAIMS, somehow, it works completely differently, that there is absolutely no correlation mathematically between separations in different charge states. And that's what allows the peak capacity, of course including mass spectrometry, but the total two-dimensional peak capacity to be multiplicative or additive with respect to the number of charge states, which I think has a tremendous power here. And as I've shown for histones, as an example of that, here, where are my histones? Here are my histones. That there are things you can separate in large charge states that you cannot separate in other, and this is just one example. We have seen many of such examples, and the more of these charge states you have, the more opportunities or shots at that goal you have. So I think this will be of tremendous power for intact proteins to try to separate different post-translational modifications and sequence inversions, because simply you have not 1 or 2 shots, but 20 shots at this goal.
I think that's a great result. I don't quite understand how you're using orthogonality still, but I think it's a really great result. Can I ask just one other question?
Sure.
What have you actually learned about Pittcon? So it seems like you've looked at our papers about this and well studied this study. So are you seeing new things that we're not seeing, or can you correlate with our stuff, or is it?
Well, I mean, whether we are seeing any new things. Well, first of all, we are seeing a lot more conformers, I think. We are seeing clearly 10 fairly major ones and some minor ones in between. For some charge states, which mostly are in the unfolded area. For folded, we still have even more peaks, but we cannot resolve them. So clearly there are even more conformers. There are probably about, based on the known instrumental peak widths that you can look at here, it's not much different instrumental peak widths from one charge state to another. Maybe it's slightly broader because of lower charge states, but not by much. So in any case, you can just look at these peak weights and look at the total weights of this distribution, and there are probably 50 conformers here that you can pull out. I know you can pull out two.
This is the last question.
Okay.
You should run the experiment where you vary the methanol water composition and favor the A state versus the A state and B state, and see if those peaks change.
Absolutely, we intend to do so. Did not do that yet. But you know, another thing is that kind of two aspects here is that yes, you can learn probably a lot more about that once you couple this to a drift tube IMS, so you can characterize the cross-section of all these separated states. And second is that the key objective here that I was indicating several times is to achieve proteomic separations of different PTMs and sequence inversions on a larger things and eventually on a top-down thing, so it's not necessarily for structural purposes. Thank you. So what are the other questions? Yes. Yes. It's a electrospray, very conventional electrospray. The flow rate is somewhere around 300 to 500 microliter per minute, so it's not quite nanospray, but close to it. Sometimes, I did not mention it, but in some cases we use multi-emitter electrospray just for slightly higher signal because of how our interface works. It's not fundamental to this experiment, just sometimes gives you slightly better signal and sensitivity. Yes.
I was impressed with the attention you gave to controlling the parameter of compensation voltage, and wonder if you have made similar analyses and improvements on the separation waveform and the geometry of the drift tube.
Well, we did some simulations that the geometry of the drift tube does not seem to be limiting at this point relatively to other problems. We nonetheless tried to make it as mirror-like as possibly our machining could and as well aligned as we could. So it does not seem that this is a limiting by this point based on some tests and simulations we did. The dispersion voltage is probably more important, and we're trying to work there. I think the two most important remaining problems, I think, are the dispersion voltage magnitude and the pressure instability. The temperature probably is somewhat secondary, simply because it doesn't change so quickly. But I think the most important are pressure and dispersion voltage, and behind that are the temperature and the mechanical misalignment or misperfection. Well, I mean, I can tell you one thing, that there is a lot more concern. I've heard that concern already from others here, including some previous talk by one other person here at this meeting yesterday. The professional safety people have a lot less problems with that than scientists, because professional safety people don't just say hydrogen, oh my god. The professional safety people look at things like flow rates, volumes, containment, and other things. So we did a very thorough study of all the safety issues related to it. I assure you the Department of Energy is a very safety-minded organization. So, for example, one simulation that was done is, what if all hydrogen tank leaks out in the room where the experiment is done? So that's obviously an extreme case, that if somebody leaves it unattended for, like, I don't know, 48 hours, and all hydrogen tanks leak out in a room, and assume room has absolutely no ventilation, so all hydrogen living in a room stays in a room. Even in that case, it will be 2 orders of magnitude below the ignition point for the explosion in the room. That's just one example. Some people say that hydrogen in the system can explode if you have a breakdown. Well, I can answer you, we had a breakdown many times when we mapped out the safe operating envelope. We never had an explosion, it's just ignition, and you have a little hydrogen torch like you would have from a little you know, flame, you just stop your hydrogen flow and that's it. Sometimes you may need to clean out and replace your FAIMS back after that incident because of the soot formed on the electrodes, they become conducting. But that's not a safety issue, it's more like operating issue. And but that problem we had only initially when we were just mapping out what voltage you can use at what hydrogen percentage. Now that we know the answer to these questions, we almost never had, for months, we did not have any such incident simply because we do not go there where we should not go. But yes, you need to pay attention to the safety, and I will tell you one situation where I would not do that experiment. If you have a very small room with poor ventilation, such that your mass spec is in some small cubby, and I've seen such labs occasionally, not with FAIMS, but just in general. In that case, it may be possible that your hydrogen will leak out in the room if, for example, you leave the experiment unattended over a long time, or something else happens. Your hydrogen through that FAIMS just continues coming, and some of that goes into the mass spectrometer and into the exhaust, but suppose that fails and it doesn't go into the exhaust and your ventilation fails, well, in principle, yes, in a small room you can achieve a critical concentration of hydrogen and have ignition and explosion with possibly fatal consequences. But that's certainly not our situation. Our laboratory is about the size of this audience hall. Yes.
I had a quick question about ion heating. You mentioned that in the hydrogen situation, ion heating is slightly more aggressive.
Yes.
I'm wondering if you have taken this sort of data from your ubiquity experiments and tried to quantify the features that are present due to this ion heating effect.
Oh, absolutely. We did so, not with hydrogen, with helium. We did so, published in this paper. Here, and we found that the heating is exactly what you expect from a two-temperature theory. It's published like about a month ago. That's with helium. With hydrogen, we did not go through such analysis for one reason, because there is not a benchmark at such a high temperatures. Basically, nobody even measured what happens with ubiquitin if you use very high gas temperatures to the point that it completely unfolds and makes so many multiple conformers, I think. Or possibly it cannot map out directly on our data because those conformers were not resolved in those data. So with helium we had a good benchmarks from David Klemmer's old data where unfolding was measured as a function of gas temperature, and we could map our data on those data. And with hydrogen we don't have such data. So it's difficult to say exactly what's going on there. However, from first principles theory that has been validated in this case, and presumably is also true for hydrogen because it's true for helium, nitrogen, and other gases, that the heating is high. But it's not that much high, it's only about 10 to 20% high. So it's difficult for me personally to believe that this small difference would result in such a dramatic gain of resolving power and annealing. So there's something else going on there probably. And Professor Cook suggested to me yesterday that possibly it has something to do with fact that the distribution of collision velocities is much narrower, and not necessarily that the mean is in at a different position of that distribution, but the distribution width is different. I have not yet thought about that carefully, but I will once I come back from this meeting. I would also mention that Perdita Baran has observed some very interesting data in hydrogen, not with FAIMS, but with drift tube IMS that seemed somewhat inexplicable in her recent paper. So there may be something else going on there on a chemical level where hydrogen somehow interacts with possibly protein outside level, which is mostly hydrogen, as you know. So it sounds stupid, but maybe there is some kind of more specific interaction of hydrogen as opposed to helium, which is of course totally inert, but some kind of, shall we say, chemistry. I'm not knowledgeable enough about that to really say, but maybe something to think about. Other questions? Okay, well, if there are no other questions, it looks like we actually had a very good discussion and came to the point where Well, we are 15 minutes over time, despite Professor Thibault not here. That's quite an achievement for the discussion. So thank you all very much for the attendance, and that concludes this symposium. Thanks.